Joining us today on Superheroes of Science, we have Dr. Allie Bramson. Allie's a new professor this semester of Planetary Science in the Department of Earth, Atmospheric, and Planetary Sciences here at Purdue University. So welcome, Allie.
Thanks. Thanks for having me.
All right. So before we get into like some of the content stuff that both you're studying and the other content things that's related to that we want to talk about, what's a new professor?
So I just started a job as a professor like 10 days ago or something. So yeah, I'm considering myself a new professor because I just started and I'm just learning the ropes of how to handle all of the different aspects of this job.
Right. I think 10 days in would be considered new in anything. It's that's fair.
Congratulations, by the way.
Totally fair. And
Yeah.
so what's your background and what research are you looking to do as a professor, and maybe what research have you done to get there?
Yeah. So my background, my undergrad degrees are in physics and astrophysics with a minor in computer science. And throughout the course of undergrad, I worked on a lot of different research projects because I knew from when I was like 4 that I wanted to be a scientist. And I was like, I want to be an astronaut because like I liked space, but I didn't know what that meant in terms of like a job for space sciences. And like, so the only thing that I ever saw was like, oh, I'm going to be an astronaut and that's what I have to do to like do space stuff. And then I like slowly figured out that like, okay, just because astronauts go into space doesn't mean they like study space. And also there are jobs just like studying space. Like that is a career path. And so, yeah, I went to college with the intention of trying to become a scientist that specializes in some type of space thing. But then I realized like space is really large and there's lots of types of space. Like there's stars and galaxies and planets and like a lot of different things. And so I worked on a lot of different research projects trying to hone in on my interests. And I started in an environmental chemistry lab actually looking at metal nanoparticles and like making nanoparticles that like could be in socks that have antimicrobial properties. And like if those like get thrown, if you throw away your antimicrobial socks, like are they going to leach heavy metals into the environment? And so I started doing research like that, and I was like, this is like too small and like obscure for me. This is like 10 to the minus 9 meters. And so then I got involved doing research with a professor in the astronomy department, which was my major, and doing galaxy clusters and like how do galaxies cluster together. So that's like 10 to the 30th meters. So I like have spanned all the orders of magnitude of the universe. And then did some summer internships through the National Science Foundation. They have these like research experiences for undergrad programs, which are amazing. And I did one at Arecibo Observatory shooting radar beams at asteroids. And then another one at the SETI Institute, so the Search for Extraterrestrial Intelligence, looking for new lava flows on Jupiter's moons. And I was like, oh my God, this is the coolest thing ever. Like our solar system and the planets and like using spacecraft data, like that is what I want to do. Like I never knew that that was like a job I could do, is like using NASA spacecraft missions and getting involved in NASA missions. And so as soon as I realized like that was a job option for me, I was like, done. This is what I'm going to be. I'm like now like, you know, I want to go to grad school and get my PhD in this, and like this is it. And so yeah, so in undergrad for me it was really like trying to find like what type of science and what type of, you know, day-to-day tasks even for science. You know, there's lab people, there's computer programming people, like science can mean a lot of different things these days. And so yeah, basically staring at pretty pictures of other planets that some NASA robots took. That's my jam. And using physics to try to explain what I'm looking at is really, you know, the overarching my research interest. And so I went to University of Arizona and got my master's and my PhD and in planetary sciences. And at that point I realized like I really want to study the surfaces of planets. Like you can see pictures of surfaces and craters and volcanoes and like trying to explain the surfaces. And so I had to take some geology classes and get caught up on geology. And so now I'm like basically in like an Earth and Atmospheric and Planetary Sciences department, even though I have an astrophysics and computer science and physics background. And so one thing that I love about planetary science is how interdisciplinary it is. It's really at the intersection between physics, astronomy, chemistry, geology, engineering, biology for like astrobiology. And I just think that's like the coolest thing ever. So here I am.
Sweet. I like that. And it is, people don't realize how interdisciplinary we are. It's everything. It's okay. People think, oh, our science, they're just like studying rocks or the weather or something maybe, but no, we are, all your fields and subjects is combined.
Yeah.
There's no such thing as like this independent, very narrow thing anymore. You have to know and collaborate with so many different people in a field.
And that can be misleading sometimes, I think, for students at school, because they go to chemistry class and then they go to algebra class and then they go to physics. I mean, they have those differences throughout the day. And so I think it's great to hear it from you that you're using all of these things, that you're not just locked into one.
Yeah.
Wow.
So what pretty pictures are you looking at now for your research what are you doing? What are you looking at now?
Yeah. So my work in grad school and, up till this point, my sort of specialty has been in understanding ice on Mars. So like, where is there water in like the subsurface, especially at lower latitudes? So at the poles, Mars has these like big ice caps that are like miles thick, sort of like we have on Earth with like Antarctica or Iceland or Greenland, and so Mars is similar, where like the poles are really cold, and so they have these like thick ice caps, and you can see the ice at the surface. And so I've been trying to understand how much ice is there actually on other parts of the planet, like at latitudes and areas like Purdue is at, sort of in what we call the mid latitudes, so not at the poles, not at the equator. Could there be ice that's stable and exists in the subsurface, just like that has a layer of dust over it that actually helps insulate it and protect it? And so I've been using like radar data from NASA missions. So the Mars Reconnaissance Orbiter has a SHARAD radar instrument that was built actually by the Italian Space Agency, and it can shoot radar beams down at the surface that actually go into the subsurface, and we can look for what's going on in the subsurface and is there ice there, and then follow up with images. So there's also the context camera and the high-rise camera on board MRO, and they're taking all these pretty pictures, and we can look, and actually there's some craters in these areas so you have one image and like it's just a flat, dusty, reddish brown surface. And then you take another image of the same area a couple months later, and all of a sudden there's a brand new crater there. There's a hole in the ground. And at these sites, the craters are actually like really bright and white and like expose the ice that's in the subsurface. That impact has actually excavated the ice and shown us there is for sure ice in these places. And so then we can keep taking pictures and watch. The ice is not stable anymore because now it's been exposed to the surface, and you can actually watch it sort of fade away as it sublimates back into the atmosphere. And that's where it's so cold and the atmospheric pressure is so low on Mars that it actually just skips the water phase. So it doesn't actually melt. It just goes straight from the ice in the subsurface and just goes straight into like the vapor form in the atmosphere. But it tells us that there's actually like a lot of ice in the subsurface. And so what I do is like I try to integrate these like image data sets with radar data sets, and I also do some like some modeling, trying to understand like how stable the ice should be and how long it's been there. And so at Purdue, I plan to continue that sort of research. It's sort of a hot topic right now, or cold topic, I guess. But it's really interesting to try to understand where these ice deposits are and what their parameters, like how much dust is in it, or just from understanding the climate of Mars, because you can't form these ice deposits today. So they are a record of previous climate on Mars. And so what record, is it trying to tell us, and trying to decipher that is part of my job and part of my research interests, as well as, if we ever send humans there one day, they're going to need water to drink, and water can be converted to rocket fuel to like send people back if they want to come back to Earth.
Really?
And so understanding where the ice is, especially at these lower latitudes where it's warmer and there's more sunlight, like it's not going to be fun to go to the poles and have like months and months of darkness in the polar night. And, your robots aren't going to like that if they're solar powered. You're going to be like super cold. So. Closest to the equator still have those ice resources is a really important topic right now for NASA and SpaceX and the other space agencies. So yeah, that's a lot of what I'm working on right now.
So
I just want to ask, when you're talking about the ice, you mean just ice like what we have here on Earth, right? Nothing.
Yeah, just water ice. So that actually brings up a common misconception is, so Mars's atmosphere is mostly carbon dioxide ice, and there is also the atmosphere is mostly carbon dioxide, and it does condense out into like seasonal ice, and there is some buried like massive carbon dioxide ice deposits in the South Pole, but actually most of the ice that we're talking about, and most of the ice even in like the polar caps, is water ice, and that was something that I think a couple tens of years ago, the thinking was it was mostly carbon dioxide ice, but we know now that it's like almost all water ice. But we don't know, like, are there like toxic salts mixed in? There's quite a bit of like perchlorates in Mars's like dust. So, and those are like, you don't want to drink that. So part of this research is also trying to figure out, like, can you just melt it and drink it and you're good to go? Or do you have to try to get out, how much do you have to like sort of clean it and filter it to get dust out or perchlorates out to make it usable? And from the climate side, like, what does that mean if you have a certain amount of dust or perchlorate mixed into the ice? What does that mean for the processes that led to like the snow, forming in this there's in the past?
And how do we know it's water ice?
That's a good question. So there's a few different arguments for like how we know that it's water ice. One is just from like a temperature point of view. So actually the mid and like lower latitudes are warm enough that carbon dioxide ice would not be stable. So carbon dioxide ice is like stable at like lower temperatures. So if you're getting temperatures as warm as the mid latitudes get, like at noon during the summer or whatever, like, yeah, you can't preserve carbon dioxide ice in these locations. And then also using like the radar and different instruments that try to look at sort of the fingerprints of the ice, what we call like spectroscopy data.
That's what I was going to ask. Are we talking spectroscopy now?
So yeah, and that starts getting outside. I haven't done a lot of spectroscopy, but like through that, and then also like the radar data, looking at what we call the dielectric properties, which is like sort of how the radar wave moves through that material, and how it sort of interacts with like an electromagnetic wave. So all those sorts of properties also tell us that it's water ice. But certainly you get carbon dioxide, like seasonal ice and stuff, those processes happening too, like in the winter, sort of a little carbon dioxide frost that forms over the course of the night, sort of like, you go outside in the morning after it's cold and you have a little frost layer. So that happens on Mars too, but carbon dioxide ice.
Oh, very cool. All right. Now, Mars being it's one planet.
Mm-hmm.
Oh, I guess I need to ask you because you're with your This would be a good one for you. Where's he gonna go? Where's it going? The Is the moon a planet
Is
in
the
your world?
like our moon?
Yes, in your world, is it classified as a planet or not?
Well, technically, I mean the moon is like orbiting our planet. So by definition it's like a moon, but oftentimes colloquially I sort of refer to like any object in the solar system that's not the sun as a planet. Sometimes it's just easier to be like, oh, I study the planets, but like,
Yeah.
actually sometimes I do some stuff with like moons or our moon, and but I would not consider our moon a planet, even though sometimes it's just
You're more the astronomer, because with your astrophysics and stuff, I'm like, well, I bet she's coming from the astronomy side of it. And we talked to a NASA geologist for geochronology, and she's like, oh, well, geologically, we would classify it as a planet because it has tectonics and core mantle, and I can't remember what it was. I need to go back and listen to her again, I guess.
And it's like basically a sphere, and
Yeah. And she's like, well, yeah, of course it's a planet. And I'm like, oh, I'm sorry.
What?
Blew my mind when she said that.
Yeah.
yeah.
Astronomers can classify however they want, but it's a planet.
I feel like we often talk about like lumpers versus splitters. Like, do people like to lump things into one category? Or are they into like splitting it into lots of different categories?
Oh, yeah.
And so, what are some of the other things that are in the solar system other than the astronomers' planets? And what are some things, and I guess kind of what's the difference a little bit?
Yeah.
Such weirdly worded.
Yeah. So I mean, at least right now, the definition of a planet as defined by the International Astronomical Union is that planets are objects that orbit the sun and essentially are big enough and have enough gravity that they've become more or less spheres or balls. And that it's also that they've cleared their sort of neighborhood, that around their orbits, they're you know, the big person in town, like they're it. And if anything else tries to wander into its orbit, that either hits it and is sort of like absorbed into the planet, or it it interacts with the gravity and it gets like shot out and ejected out of its orbit. Like, bye, get out of my space. So planets, that's sort of the definition of a planet. And so by that definition, we have 8 planets in the solar system. And we've got the terrestrial planets. So that's like Mercury, Venus, Earth, and Mars. And those are rocky and have metal cores. And those are rocky and metal, like have metal, because they're thought to form in the sort of inner part of the solar system close to the sun. So it was too hot for like ice and stuff to stick around. But meanwhile, when you start going to the outer solar system, then you've got the gas giants and the ice giants. So the gas giants, Jupiter and Saturn, are more made of gas that was able to sort of clump together and stick around. And then if you go even further out, so now Uranus and Neptune are considered more to be like ice giants, a separate category than gas giants, and that's because at that point it's cold enough in the solar system that they were able to form from lots of ices. It was cold there, and so the ices didn't just like get it wasn't too hot for them. Yeah. And sometimes it's called like that line of where like ice can exist versus where it's too hot is sometimes called the snow line. But yeah, so the ice giants are made of like water and ammonia and methane ice. And then outside of Neptune's orbit is, so there was Pluto, and we considered Pluto a planet. Like Pluto was a planet when I was growing up. You have the placemat that you're eating on when you're, eating breakfast on. It has all the planets on it. At least I had that, but I was, obsessed with this space since for forever. And so, yeah, past Neptune, there's all these like other objects that we now know of. Like in the last 20 or 30 years, we now know there's tons of objects out there past Neptune, not just Pluto. And actually some Eris is even bigger than Pluto. And so that kind of caused this like, well, okay, now we know there's a lot more out there. Do we classify those as planets, or do we make them into their own category? And so that's where, there's sort of this dilemma, and like lumpers versus splitters, and how do we classify a planet? And so because there was all these what are called trans-Neptunian objects found, several of them being really big objects. Ultimately, the International Astronomical Union, the IAU, that's sort of tasked with at least trying to come up with conventions for the community to use. They decided to, okay, with this new knowledge that we have, let's make another category of object. And let's call it like dwarf planets or like minor planets. And these are things that still orbit the sun. They're still large enough to be round sort of balls, but they're on the small side, and they can orbit with other objects. They didn't need to have cleared their orbit. And Pluto fits into this category because its orbit is oval or egg shaped, and it crosses Neptune's path sometimes. And there's also all these other trans-Neptunian objects out there. And so that's where, dwarf planets sort of became another category in the last, 15 years or so. And in addition to that, there's the asteroids and comets as well. And so we have our asteroid belt that's sort of in between Mars and Jupiter. And that's a bunch of like rocky fragments that are sort of left over from when the planets formed. So there was a bunch of stuff, going around in like our solar system area, and they were colliding and clumping together, and eventually the big ones became the planets. But a bunch of the remnant rocky and icy material is still left over. We still have a lot of it in the solar system, and so a lot of that is in the form of rocky objects in the asteroid belt, and then also icy objects out in the outer solar system, like in the Kuiper belt, where Pluto and these trans-Neptunian objects are, and also the Oort cloud, which is a bunch of icy stuff that's sort of like all enveloping our solar system, but like sort of it's a big blanket of icy material that surrounds our solar system. And comets come usually from like the Kuiper belt or the Oort cloud. It's like these icy objects that are on these wacky orbits, and sometimes they like happen to wander into the inner solar system, and then they light up when the sun starts like causing the ice to turn to gas, and that's where you get the tail. So if anyone saw like the comet a couple of weeks ago, that happened to just like make a visit into the inner solar system after hanging out really far away for a while, and then its ice was like, I'm not stable, this is too hot for me, bye.
Well, why Mars? Why not like Titan or Europa? Why Mars? Why are you studying Mars?
There's lots of data.
There you go.
I mean, I think Titan and Europa and Pluto, and I don't know. Like I've been asked like, what's your favorite planet or what's your favorite solar system object? And like, I can't decide. They're all so cool for like such different reasons. And so I think, Mars, because it's pretty close to Earth, we've got like a really good cadence of sending missions there. So we've got like decades of monitoring, and so we can actually see changes occurring on Mars. And it's sort of cool to compare and contrast and be like, oh, this place is like so like Earth sometimes, and the processes are so similar, but at the same time, it can be so exotic and different. And we have enough data, and we've got regular data sets that we can find these like new impact craters that are exposing ice, and we can see dust devils forming and going across the surface, and dust storms that are, it's an active place. And so
I guess I never thought about it having wind.
Yeah.
A dust devil.
Yeah. There's like, we've got like you can find like GIFs of like dust devils going around the surface that the rovers have seen, and you can also see them from orbit. And the thing is, the atmospheric pressure is so low, it's like less than 1% of Earth, that the dust devils actually get to be so high they would be taller than Mount Everest on Earth.
Oh my gosh.
So Mars is a cool place, and it's super active. You can see like some sand dunes that move. Mm-hmm. There's like these seasonal frost processes that like deposit ice layers. just like overnight or in the winter. So it's a really active place. It's close to get to. It's relatively easy to get to. You can get there in the course of like several months, whereas, the missions to Pluto are hard to do because it takes so long to get there. And which is one thing about this job is it like requires really long-term planning, because you have to be like, you have to be in it and be like, all right, I'm not going to get this like data for, if this mission is selected by NASA, maybe it'll launch in like 2030, and then I'll get like my image that I need to do my study in like 2036. And so I think I'm certainly interested in like all of the solar system, and I've been involved in studies like trying to understand carbon dioxide ice deposits that form in craters in Uranus's moon. One of their moons called there's a moon called Umbriel, and it has this big crater called Wanda, and it has like this bright deposit. So first of all, we barely have any data for out there in the solar system. The Voyager missions went by there like back in like 1986, and we have like one image of one part of the moon, and that's it. And that's like all we have to try to study. And there's this like bright ring inside the crater. And so I was involved in a study with another professor actually at Purdue, Mike Sorey. We both just started here, and we found that the crater is probably full of carbon dioxide ice, and so we called it a Wanda full world because the crater is named Wanda, and thought we were really clever, and so certainly I've been involved in studies, not just Mars, because I think the whole solar system is really cool, but Mars just does have a lot of data because it is just relatively easier to get to than sort of the outer parts of the solar system. And at this point, there's we want to continue that monitoring that we already have and not lose that data set when, trying to understand these active processes that are affecting Mars. But yeah.
Well, from your research and things, from your perspective, where do you see, what are some implications of the research that you're doing?
Yeah, so I mean, one is just like on the human exploration side. I can't say, I don't know when it'll actually happen, or if when we'll ever get to the stage of sending humans to Mars. Hopefully sooner rather than later. But it's going to be a really hard task. Like, we haven't even gone back to the moon since, in the 60, 70, 60 years or so. And so yeah, I mean, we'll see when it happens on Mars. It would be awesome. But certainly, understanding where the ice is that is an accessible resource for human explorers is one big implication. And another is in terms of like, if you understand ice stability and where ice is on the planets and on Mars, that can tell you just about processes that shape all the planets, including Earth. So, if we can better understand Mars's climate, especially because it's a simpler system, it doesn't have an ocean, it doesn't have life, it doesn't have humans. It's a simpler system, but to some extent, in one way, it's more extreme. So the axial tilt of a planet, and like how eccentric the orbit is, and some aspects of the planet vary sort of over different time scales, like 100,000 years or something. The axial tilt, or how much the planet is tilted, we also call it the obliquity. That affects where ice is stable. And so even the ice ages on Earth can be somewhat attributed, they're called Milankovitch cycles, to like very subtle variations in like that tilt of the planet. Because if you're more tilted, then the pole is getting more direct sunlight, and all of a sudden, ice isn't as stable at the poles. And if you have no tilt, then your equator is just getting blasted with sunlight, and your poles are really, really cold and experience like more extreme winters. And so this tilt is really important and can cause ice ages on Earth. Meanwhile, on Mars, because Mars doesn't have like a big stabilizing moon like we do here on Earth, its tilt actually like sort of goes a little crazy and can be like, it's thought that in Mars's history, it's like been as high as like 60 or 80 degrees. Like it's almost been tilted on its side. And then sometimes it's just like perfectly straight up and has no tilt. And so it's actually an awesome sort of laboratory for studying how do these natural processes affect climate change on another planet, so that we can sort of subtract those out from Earth. Like we know that there's natural variations that occur because we know that the tilt is changing. We know that subtle eccentricity changes happen, and that can drive natural climate change. And so if we understand these processes, we can sort of subtract them out and see, okay, what are the processes and timescales and stuff of like the climate change that we're experiencing now, and how does that compare, and start making more connections to these other factors like humans.
All right, so that blew me away just a little bit, because this is the first time I've ever heard someone discuss studying another planet to better understand the Earth. We always do the opposite. That's all we talk about is we study the Earth so we can better understand processes and how things happen. But this is the first time I've heard someone talk about, we're studying, we study the tilt and things like this to better understand what is happening naturally to see our impact. That's the first time I've heard anybody say that. I'm just like, I'm done for the week. Mercy. It's too much to think about that.
Yeah, we're towards the end of the week anyways. Yeah.
That, and I didn't. It's you said like 3 or 4 things in there that I'm like, what? You might be coming back. You might have to do an episode now because I first of all, I didn't realize our tilt wasn't like. I didn't know there were small variations in the tilt.
I didn't either.
I didn't know the moon was help keeping our tilt stable.
Right.
I'm like, when you said that, I was like, what?
Yeah. Thank you, moon.
That and keep going. What? Wow.
That was awesome. Yeah.
Yeah, the moon, like the Earth's tilt is at like sort of 23 or 24 degrees. And that's the whole reason why we have seasons, right? So like, because we're slightly tilted, sometimes, we're in the hemisphere that's pointed towards the sun, and then on the other side of the orbit, we're facing away. And because of our moon, we only like change our tilt by like maybe 1 degree. Whereas Mars is just like, well, I'm going to do what I want to do.
Wow.
What?
That's really cool.
So yeah, go out and thank the moon tonight.
Definitely.
I think I might just have to do that. That waning gibbous. But okay, well, thank you. We really appreciate your time.